All right, this is problem 4 number 7. Let's take a look. So we're given a basis. It looks like an R2. Suppose the coordinate mapping determined by B is a linear transformation from R2 into R2. This mapping must be implemented by some 2 by 2 matrix A. Find it. Okay, and then it says, hint, multiplication by A should transform a vector x into its coordinate vector xb. So they want us to go from an arbitrary vector x into its coordinate vector. All right. And you might remember if in the coordinate vector is with respect to basis B. You might remember by definition, let's just say, for example, V1, V2 is a basis for some vector space. Well, that means any vector in the space can be written as some constant times V1 plus some other constant times V2. Well, you call that 2 by 1 vector matrix the coordinate vector of x with respect to basis B. And this is the notation for it. All right. So notice the B subscript, because it does depend on the basis. And it does depend on the order of the basis elements too. So that's a coordinate vector with respect to a basis. All right. And in general, you can say the following is true, and we're going to need to use this fact. And I think you actually need this fact on problem number 6. Whenever you go from the coordinate vector of x with respect to basis B to a representation of that vector with respect to the unit vector, or I should say the regular unit vectors in Rn, you have to multiply that coordinate vector by some matrix. And that matrix is called the change of coordinates matrix. All right. And it really just consists of columns that are the basis elements of B. So, for example, we might assume that B is equal to V1, V2. Those might just be basis elements of B. Well, if we make a matrix out of that, and remember V1 and V2 are column matrices, and we multiply that by the coordinate vector of x with respect to basis B, we should get back the regular representation of that vector in the vector space. So that's kind of the basic equation that you start off with. Because, you know, for example, this coordinate vector of x with respect to basis B might be C1, C2. And remember, the coordinate vector, the elements are just the coefficients of the basis elements, okay? So notice that if you actually multiply these two guys together, and these are column vectors, but you're still going to end up with C1, V1 plus C2, V2. And that is the original one representation of vector x, okay? So this is kind of the key equation that you use in number 6, but you also use it in number 7. Because in number 7, they don't want us to go from the coordinate vector to x. They actually want us to go from x to the coordinate vector. They want us to go backwards, okay? So here's what you do. You start off with the equation, this equation. And in order to go from x to the coordinate vector of x, multiply this equation on the left by the inverse of that matrix. All right? And it will be a square matrix. And that'll cancel it out and turn it into the identity. So another way to write it is like this. So it's really the inverse of the change of coordinates matrix times x. That's how you go from vector x to its coordinate vector. So let's use that fact in this particular problem. Now in this particular problem, the basis is this. Okay. And those form the columns of the change of coordinates matrix. All right, so that's what PB is. All right, so we just have to find the inverse of this matrix, essentially, and then multiplied by x in general. And that's what they're calling A in this problem, is P inverse sub B, the inverse of the change of coordinates matrix. So there is a formula you might remember for the inverse of a 2 by 2. It's pretty easy. It's just 1 over the determinant, which is -4 plus 5. And usually you switch these two elements around and change the signs of these other two elements. So that's just going to turn into a 1. So here's your matrix. And that's the matrix A that they were looking for in the problem. That'll take you from a regular vector to its coordinate vector.